Welcome back, students. Today we begin with the basics of digital systems, wherein we start with logic gates. What are logic gates? Gates are digital circuits with one or more input voltages but only one output voltage. Besides one, there is only one gate which has a single input and a single output. What are gates and why are they important in digital electronics? Gates are important because they allow us to make decisions, and they are the basic building blocks wherein the concept of artificial intelligence starts. Once you take a lift, the lift says that maybe 8 persons or maybe 1000 kilos. So how does a lift know what is happening? It has a pressure sensor, and with the pressure sensor transmits a signal to a gate, which then decides whether the lift can be allowed to move or not allowed to move. A microwave, again decision making, or a washing machine, decision making. You put a couple of clothes in a washing machine. If the weight is more than the weight that the washing machine can process, then the washing machine does not run. So all decision making, intelligence and everything is governed by the basic blocks of logic gates. The basic gates that we have are the AND gates, the OR gate, the NOT gate, the NAND gate, the NOR gate, the XOR gate and XNOR gate. Basically, the gates AND, OR and NOT can be combined to realize the other gates, and as we will see later, the NAND and NOR gates are also known as universal gates. AND gate. Typically, AND gate is a gate that may have at least 2 inputs and one single output, and we say that the output of AND gate will be high if and only if all its inputs are high. For an AND gate with 2 inputs, as we already know, in digital or the binary system, we have, if there are 2 inputs, there are 4 possible combinations: 0 0, 0 1, 1 0, 1 1. So, as per the expression or definition of AND gate, we know that the only input combination for which the AND gate will give you a high output will be when both inputs, in this case A and B, are 1 1. So 0 0 gives you 0, 0 1 is 0, 1 0 is 0, only 1 1 is 1. In actual practicals, we use 74XX series of integrated circuits. So AND gate, we have IC numbered as 7408. So basically it is a quad 2 input AND gate IC. Quad means there are 4 AND gates within the IC, each of 2 input and 1 output. So AND gate, how do we actually realize the working of AND gate? First, as shown here in the figure, we see that there are 2 diodes which are fixed, their ends are fixed to the common power supply. So the diodes, how do they actually realize the working of AND gate? Now the diodes, the 2 inputs are shown as A and B, wherein a power supply is fixed. Typically the power supply is of 5 volts. When we give A0, B0, then due to the power supply at the top, the current flows through both the diodes to the ground. 0 0 input means that both the inputs are at ground. When both the inputs are at ground, then the current, both the diodes get forward biased and when they get forward biased, they offer minimal resistance. Ideal diode would be offering 0 resistance, but we know that diodes are not ideal, and hence they get forward biased while offering minimal resistance to the flow of current, and that current then goes directly to the ground. So, at the output we would always have, there would be no voltage drop, and since no current is flowing, and hence the output will be 0. Next combination is A0 B1. When we have A0 B1, then the diode connected to the A input is forward biased, whereas the diode at B is reverse biased. That is because it does not have a potential drop across it. At both the ends of the diode, you have high values of power supply, and hence the diode at B does not conduct. However, the diode at point A conducts. When it conducts, the current finds the path of least resistance and goes to the ground, and therefore again there is no voltage drop across Y, since no current flows, because current has already found the path of least resistance through A, and therefore again for the input combination 0 1 A0 B1, the output Y is 0. Now we change to the third combination, wherein A is 1 and B is 0. Again the same story as per the previous case repeats, and we find that for A, the diode does not conduct, since both ends of the diode at A are at high potential. For point B, we have forward biasing of the diode, because current can flow through the diode to the ground. However, the story is the same at the output. A does not conduct, but B conducts, and therefore the current chooses the least path of resistance through B, so that output Y again comes out 0. For the last case, when both A and B are 1, then when we see that both the diodes at A and B are having high potentials at both the ends, and they cannot conduct. Therefore, current from the voltage source passes through the resistance to the output Y, wherein we will have the load resistance, and therefore we have a voltage drop across the load resistance, and output comes out as 1. It is also clearly seen in the timing diagram that whenever only A and B both are high, that we get the output Y in a high state. If both AB or any of either of AB is 0, then output Y gives 0. So, AND gate is realized, 2 input AND gate working is realized using the same configuration of both the diodes, and we see that it gives a high output if and only if both the inputs are high. Now we move to the OR gate. OR gate gives a high output if and only if any or all of its inputs are high. We put this one in a different fashion. We put its definition as OR gate gives a low output if and only if all of its inputs are 0. So, OR gate at the minimum will have 2 inputs, and it can have any number of inputs depending on the fan in requirement. So, the typical truth table for OR gate can be seen that for 0 0, 0 1, 1 0, 1 1 combinations, the output is 0 when both A and B are 0. Otherwise, its output is always fixed at 1. In the common laboratory, we use the IC 7432. Again, it is a quad 2 input OR gate. That means there are 4 OR gates in that IC, each of 2 input and 1 single output. The OR gate can be realized again using the diodes. In this case, it may be seen that unlike the case of AND gates, we do not have a power supply directly connecting the diodes. Okay? The inputs in this case, like the previous one, is A and B. So, when A is equal to 0 and B is equal to 0, both the diodes at point A and point B are not forward biased and hence do not conduct current. Therefore, the current through RL is 0 and therefore, the voltage drop across RL is 0. For the input combination A equal to 0 and B equal to 1, we see that the diode at point A does not conduct. However, the diode at point B is forward biased and therefore, the current passes through the diode at B and it then passes through the load resistance RL, giving us a voltage drop, and that voltage drop is shown as state 1. It may be noted that the current from point B will not go into diode at A, because for the current the diode at A is reverse biased. Hence, the only path that the current can take is from the point B. The diode at point B is through RL. The timing diagram can also be interpreted as the output would continue to remain high till the time both the inputs A and B are 0 simultaneously. Now, we need to go for the basic concept of bipolar junction transistor before we can move on to the NOT gate. In this case, we need to understand that the bipolar junction transistor with the acronym BJT has 2 junctions. One, the junction between emitter and the base, and then base and the collector. So, emitter, as the name suggests, emits the majority charge carriers. So, if we take the case of NPN transistor, it would be electrons. The electrons would be emitted from the emitter. They would pass through the base, which anyway is very thin and lightly doped compared to the emitter. A few recombinations of electrons and holes would take place in the base, and most of the electrons would then pass on to the collector. Collector, being reverse biased, would attract the electrons by providing them with kinetic energy in the linear direction. So, we can understand that this transistor can actually act as a switch. That is, when the emitter base junction needs to be forward biased and the base collector junction needs to be reverse biased. So, when we have current flowing through, the maximum current flowing through the BJT, then we say that it is in saturation. When we have almost 0, that is negligible current flowing through the BJT, we say it is in the cutoff. We do not use this BJT in the active region in digital electron. BJT's normal function is in amplifiers. However, if its function is limited to only saturation and cutoff, then it acts as a switch, and then its characteristics can be used for digital electronics. So, we come to the next gate, which is the NOT gate. It is the only gate which has a single input and a single output, because the output is just the complement of the input. We must remember that this is the binary system. So, there are only two bits, 0 and 1. So, if the input of the NOT gate is 0, then its output would be 1, and if its input is 1, then the output would be 0. The circuit here shows how the NOT gate is to be realized using a BJT. It may be seen that the BJT has two parts, one the input part having the base and the emitter, and the output part which has the collector and the emitter. This is the common emitter configuration of the transistor or the BJT. So, what we have at point A are only two inputs, either it is 0 or it is 1. As per the figure, initially at the point A, it is the ground connected, and therefore, it is 0 volt. When it is 0 volt, then the base emitter junction is not forward biased. If it is not forward biased, if the base emitter junction is not forward biased, then there is no emitter current. If there is no emitter current, then there is no collector current. If there is no collector current, then from VCC the current would be coming, and collector being reverse biased, no current being present, there is no voltage drop, and therefore at the output Y, where we have the RL, the whole current emanating from VCC would pass through it, and therefore we would have a high output. So, with the input A being 0, we get Y equal to 1. It is not that we have been able to generate energy, because finally the electrical energy is being supplied by the fixed bias of VCC. In the next case, the A may be made 1. So, in that case, the base emitter junction gets forward biased, and we have the current IE. This IE would pass through the base and reach the collector with a magnitude which is almost compatible with that of the emitter current, since we know that IE is equal to IB plus IC. So, therefore, IC will always be compatible in magnitude with IE, since base current is very small and base area is also very thin. So, right now what we have is IE compatible to IC, but IE is there at a junction where the junction is forward biased, and we all know if a PN junction is forward biased, then it offers very small resistance, whereas IC, which is compatible with IE, is there in the collector region, which we know is reverse biased. For reverse bias, we know that the resistance is very high. So, therefore, what we have here is high current in a high resistance region. Therefore, the potential drop across the resistance is high in both the ends. At the top is the VCC, and the voltage drop here at the collector is also high. So, therefore, high minus high is low or 0, and therefore, for a high input at A, we have Y as 0. So, NOT operation is like this, that A is 0, then Y is 1. If A is 1, then Y is 0. For OR operation, we know that A is 0 and B is 0, then Y is 0. If A is 0, B is 1, then y is equal to 1. If a is 1, b is 0, then we know that again y is 1, and if both a and b both are 1, then of course it is 1. So, final summary of AND operation also, that if it is 0 and 0 for a and b, the output is 0. If it is 1 and 0, output is still 0. If it is 0 and 1, the output still remains 0, and the output becomes 1 when both the inputs of AND operation are 1. Thank you so much.